Hello and welcome to Cup of Cosmology, the place for all your questions about the universe. My name is Diana Hooper and I'm a postdoctoral researcher currently at the Helsinki Institute of Physics over in the University of Helsinki in Finland. And I am a cosmologist. So that means that I study the universe, the contents of the universe, how everything evolves, how everything interacts, all of the cool stuff happening inside the universe. And I really like being a scientist. I like being a cosmologist. I get to work on some incredibly fun topics and chat to some really cool people. And on the topic of chatting to people, I love talking to people about science and about cosmology, about academia, about all of the stuff happening inside that nice big fancy ivory tower that I get to work in. Went on a tangent already. Well, not even 2 minutes in and I'm already on tangents. Hey Scott, great to see you in first today. Really nice to see you. So yeah, I'm a cosmologist, I'm a theoretical physicist, I study the universe and stuff happening inside the universe. And I love jumping here on YouTube, on Twitter, wherever you're watching from, to chat about all of the cool things happening inside the universe, to answer any questions you have and just have this conversation about fun stuff that I work on or stuff that I don't work on. It's always fun to see what kind of questions people throw my way. Hey James, great to see you as well. Very nice to see you. Got some people in here who have been around in Cup of Cosmology for quite a few years now. Nice to see all of the regulars coming in, as always. So sometimes on Cup of Cosmology, we tackle specific topics. Sometimes I have guests on. Sometimes I have guests who tackle specific topics. Sometimes I prepare my own topics. Today, we have none of those. Today, we have a completely improvised stream. So this is just going to be a general ask me anything about the universe, about cosmology, about physics, about my research, about academia, about me, anything you want. Today is a general ask me anything. I know I did mention that I had a guest scheduled today. We had a last minute change of plans. As always, Cup of Cosmology should never ever be an obligation for anybody. So last minute changes of plans are always perfectly fine. But that does mean that I didn't have time to prepare a topic. So we're just going to wing it today and see what happens. So any questions you have about the universe, about anything you want, now is the time to ask. You can even ask me about blue dwarfs, although I will just point you to the video where that was covered, even though that video is actually not on the YouTube channel to the best of my knowledge yet. I need to upload the video where we discuss blue dwarfs to YouTube so that then I have a reference for any time Scott asks me about blue dwarfs again. So yeah, I'm a cosmologist. I study the universe. I've been thinking lately about the different types of things I've studied because throughout my career, I've actually worked on quite a few different topics, which is really fun. And I was doing a recap recently, going like, what have I worked on? What are my different topics? It was really fun to remember like what I've worked on in the past and where I am now and how my research plan has changed. Because there's been a bunch of times in my career where I thought, I found the thing I want to work on, and then I find something else. And it's always fun to go after shiny new topics and chase new ideas and try out new things. So I was thinking back, my bachelor thesis, the first like big project I did was on exoplanets. So much smaller scale than cosmology and stuff like that. Exoplanets, looking for planets outside of the solar system. I helped assemble a little baby telescope and plow through the data looking for exoplanets. We didn't find any, but it was fun nonetheless. And then, at some point I moved onto the cosmos. And inside the cosmos, there is a lot that one can work on. In fact, if we bring up the history of the universe, I think I prefer this image, actually. Let's switch to this image. History of the evolution of the universe, right from Big Bang on the left to where we are today on the right. Looking through this, we start with like cosmic inflation. I've worked on that. Particles form, kind of worked on that. Dark matter, worked on that. We have the Cmb in the middle, worked on that. Galaxy evolution, worked on that. So it's fun to think of all the different cool topics. So I'm just mentioning this to tell you all of the things you can ask me about. Basically, anything on that image, you can ask me. And, I don't have all the answers because there's a bunch of stuff there I haven't worked on, but there's a bunch of stuff I have worked on. So as always, any questions, even about exoplanets, you can ask me any questions you like. Isn't it cool that there's a type of star that we don't have any of because the universe isn't old enough? It is very cool. So blue dwarfs are hypothetical stars that could exist, but they take longer to form than the age of the universe. So to the best of our knowledge, the universe is 13.82 billion years old. a lot has happened in these 13.82 billion years, as you can see here in the image. A bunch of stuff has happened, a lot of different stuff in these 13.82 billion years. Now, blue dwarfs are a type of dwarf star that could hypothetically exist within our universe. However, they take more than 13.82 billion years to form, which means they couldn't exist in the universe as we have it today. But maybe in the future, we'll reach this stage of stellar evolution where we have blue dwarfs. So it is nice to think about the fact that, everything we see now is not necessarily everything that could exist. Of course, if we want to go to longer timescales, then we can also start asking the question of what if the proton decays? And there's a fun one to think about. So the proton is one of the particles that makes up pretty much everything that we know of. Protons are stable, we think, at least on lifespans of the universe. Anything beyond that, maybe they should be stable. It's fine, not something we need to worry about immediately. Did they ever figure out what was up with Tabby's star? I love Tabby's star. Tabby's star is great because it got a lot of people talking. And, I'm always happy to have people talking about cool stuff happening in space. Even if sometimes the conversations are a bit odd, it is always cool to have more people interested in what's happening out there. So Tabby's star is a star that we've been able to see within the solar system. Not within the solar system, sorry, within the Milky Way. There's only one star in the solar system. Within the Milky Way, we've been able to see a star which we know as Tabby's star. And when we look at the light coming from Tabby's star, the scientists, were able to see that the light in front of the Tabby's star decreases. So the amount of light we receive from Tabby's star was decreasing. Not constantly, there was just like this periodic decrease. Now, usually what this is telling us is that something is moving in front of the star. This is actually one of the ways we try to find exoplanets, or planets outside of the solar system. If you look at the light coming from a distant star and something moves in front of that star, you are going to receive overall less light. If this happens every 365 days, for an example, then you might say there's a planet orbiting around this star on the same plane that we're observing it, and its orbital period is 365 days, and then once a year it blocks out the light from the sun or from the star. So looking at the light curve, so how much light we are receiving as a function of time for Tabby's star, people were able to see, I realised I forgot to silence my phone today, people were able to see that there was actually something passing in front of Tabby's star. But the way the light curve behaves, so the amount of light we receive over time, was not consistent with a planet. And this is where people said, okay, well, scientists said this could be a lot of different things. And then and then there was one scientist who made a flippant offhand comment to a journalist, like, it could be anything. It could even be something like an alien megastructure. Or actually, I think the phrasing was, we can't rule out that it's an alien megastructure. And of course, what the press ran with is scientists say they found an alien megastructure around Tabby's star. Yeah. So it's often the thing that people's research can be taken out of context in the media. And it can be a bit frustrating sometimes. And this happened with Tabby's star. Now, there were 1,000 different possibilities. The idea of an alien megastructure was pretty low down on the list, but of course, non-zero probability, but a very, very, very small probability. By now, it does seem, so the reason it looked like an alien megastructure is because it could be compatible with what is known as a Dyson Sphere, which is a hypothetical sphere an advanced civilization could build around a star in order to harness the energy. So you'd basically have the energy of the star. So you'd basically have a swarm of satellites around this star that could then use its energy, like solar capture its energy and transport it back. Is one of the ways that advanced civilizations might sustain their energy needs. We're nowhere near technologically advanced enough to build a Dyson Sphere yet. So when people said alien megastructure, what they were thinking of is potentially a Dyson Sphere. However, it did look like in the end that the light curve from Tabby's star was much more consistent with a cloud of dust, basically. We say dust, everything in the universe that is not big enough to be a planet, we call dust. But basically, like a cloud of debris. What could have happened is a comet that got burnt up close to the sun, close to the star, or even some asteroids that crashed into one of the other planets in the system and then got flung about there. But it did seem like there was basically a big debris field passing in front of the star, which is much more plausible than an alien megastructure. So while we can't rule out that it's an alien megastructure, to the best of, I think currently the leading idea is that it is actually a debris cloud from some rocks and gas and dust, either from a comet or from an asteroid or from something that is now passing in orbit around the sun, around the star. Still very, very, very interesting, but potentially less eye-catchy and headline-worthy as alien megastructure. How would a Dyson sphere be better than normal solar power except for magnitude? Well, for one, the magnitude, and this is the thing that we're talking about, orders of magnitude difference here. Like if you could build this Dyson sphere right up close to the star in question, you can get a huge amount of input from the star. Now, the solar panels are an amazing achievement that we have here, and it's something that more people should use and embrace. And solar panels are definitely one of the energy systems of the future. And today, actually, not just the future, there's something that we can get now. The problem always is storage and transport and having enough electricity. Whereas if you have the Dyson sphere directly in front of the star, you can really maximize the amount of energy you're absorbing. And then, of course, the question is, how do you transport that? How do you use it? Do you actually need to transport it back to Earth or back to the planet in question? Or if you're, a spacefaring civilization at that point, then you can use the power harness from the Dyson sphere directly to power your spacecraft, potentially. Wouldn't a Dyson sphere have a different pattern? I think the conclusion there was that the Dyson sphere or a Dyson sphere under construction would have the same overall pattern or a similar pattern to what we saw in front of Tabby's star. Not the same, but similar. But yes, I have not looked into Dyson spheres in quite a while, so half of what I'm saying here is like somewhere in the back of my brain where I'm just picking out pieces of Dyson spheres, like not literally, but just picking out the informational pieces on how to build the Dyson sphere. As always, there is an excellent course Gesagt on exactly this topic. For anybody who doesn't know, course Gesagt is the second best YouTube channel out there, because the best one is obviously Cup of Cosmology. Other one might be biased in that opinion. Course Gesagt is an amazing YouTube channel that does a huge amount of science communication videos on a bunch of fun topics with really cute animations. And they have a whole series on Dyson spheres and alien megastructures and stuff like that. So it's definitely worth checking out if you want to learn more about Dyson spheres. And if that's not enough, they also do very cute posters of Dyson spheres. And I had to resist the temptation to buy that poster again when I ordered more merch from Quizkazact a few days ago. But that's me rambling on a tangent there. Hey, Nadia, great to see you from New York City. I do like New York. It's a great place. Hello from Helsinki. Great to have you here. We're doing an Ask Me Anything. Any questions about the universe, go ahead and ask. I will try my best to answer. Or about science, about academia. It's a general Ask Me Anything today. If I was an alien megastructure, I would mimic my appearance and look like a debris field, just saying. Yeah, it's also the thing, right? If you are in an advanced enough spacecraft or a megastructure, could you hide the signature in a way that unadvanced species or less advanced species wouldn't be able to measure it? Potentially. So then it brings us back to, does Tabby's star have a super advanced civilization that we have seen no other trace of, maybe because it's staying quiet from us? Or is it a debris field, which we know there is a lot of in the universe? And then you reach the conclusion that it's probably not the alien megastructure. We should mine Mercury to get raw materials for the Dyson sphere. That is one proposal, I believe, from the Quizkazack video. The problem there is, how do we get to Mercury? We're still trying to figure out how to get to Mars. Mercury's a bit further away. So we sent a spacecraft there, but yeah, it's very difficult because space is very, very, very big. And there is a lot of empty space. And we think Mars is close by because it's our neighboring planet. Mars is far away. Venus is far away. All of the planets are far away from us. It's very difficult for us to actually go to these other places. We barely explored our solar system, and there's a whole universe out there waiting for us. Did you get one of the cute stuffed black holes? I did, yes. So Quizkazak has a stuffed toy of a black hole on one side, a white hole on another side. How could I resist? Yes, I will absolutely be using that as a prop once I get it. So once I get my stuffed black hole, I will absolutely bring that to the streams and use that as a prop. So yes, I feel like you know me well, Scott, because that was the first item I added to my cart. And the calendar, because of course I need a new calendar. Always need the Cosmological calendars. And you can never have enough much. Not we per se, but future humans, assuming we don't go extinct before then. Yeah, I mean, assuming humanity can avoid the impending crisis that we have created for ourselves in the form of the climate catastrophe that is approaching and that we should be dealing with, assuming we can survive the climate crisis and the climate catastrophe and the ensuing, extinction level events, yes, future generations should absolutely try to mine materials from Mercury to build a Dyson Sphere. That would be the most reasonable way of doing it, because transporting stuff from here to the sun to build a Dyson Sphere would be very, very difficult. However, if you could set up a base on Mercury, like a mining base on Mercury, you could directly produce the materials you need, hypothetically speaking here. You could produce the materials you need for the Dyson Sphere directly on Mercury and then launch them up to the sun. It would be much more cost efficient and probably the way to go if we ever reach the point of being a species that can actually have the technology and the ingenuity and the capacity to build a Dyson Sphere. I think mining Mercury is the way we would do it, because it wouldn't really make sense to send the raw materials from here. But of course, that assumes that we actually have a future. I wonder what the painting is of. If you mean this painting behind me, this is a picture from Doctor Who. It's the exploding TARDIS done in Van Gogh style. It's from season 5 of Doctor Who. It's a important painting in season 5 of Doctor Who, and I have a poster of it. It is technically not my poster. I just kind of stole it from my partner, and it's mine now. So it's here until it gets reclaimed. But yes, I'm a huge Doctor Who fan. Actually, today I'm wearing a Doctor Who t-shirt. I have a Doctor Who necklace, and I'm sat in front of my Doctor Who poster. So the painting is the exploding TARDIS done in Van Gogh style from Doctor Who season 5. And then the thing you can see up there is my Christmas wreath made in origami Christmas wreath in non-binary colors. It was supposed to be a Christmas wreath, and then I decided having a non-binary wreath on my wall is kind of cute, so it stayed up all year round. And next to me is the Cosmological calendar, and I'm not going to show you the rest of the place, but I do have a lot of paintings and Lego spacecraft, Lego International Space Station, a lot of stuff. I'm easily distracted today. You asked me about the painting, and I'm going to start rambling. Is our ability to determine the density or the mass of something in space require us to see how that object interacts with other bodies? Can we figure out a rogue planet mass if it wasn't near other objects? This is a great series of questions here, James. Really, really interesting. And it's always a problem of how do you measure something in the universe? Because you can't really pick it up and put it on a scale, right? And it becomes quite hard to measure the density or the overall mass of objects. And usually the best tool we have to do this is seeing how an object interacts with things around it. So if you want to measure the mass of the moons of Jupiter, for an example, you'll look at Jupiter, you'll look at how long it takes the moons to go around, and from there you can get their mass and the distance. Usually we measure an object based, to measure the mass of the moon, we can't really go and pick up the moon and measure it, but we can measure the effect the moon has on us, on the tides, on the planet itself, and we can use that to get an idea of how big the moon is. Same with the sun, same with all of the other objects in the solar system. So we always do kind of use the fact that objects with mass will have a gravitational force on each other, and this is what we can use to measure things. Then with things like stars, we have other options based on the temperature of the star, which we can get based on the spectral decomposition. We can get a good idea as to how massive stars are, because there's usually a relationship between the mass of a star and its temperature. So this is something we can calculate. So for some things, we have strategies like stars, objects that emit light. If we know how they emit light, we can figure out their mass. But a lot of objects, like your example of a rogue planet, it would be quite difficult to figure out the mass of a rogue planet if it's really doing its own thing. So a rogue planet is a planet that has either been kicked out of its solar system or kicked out of its galaxy due to some random gravitational effects. For an example, planets crashing into each other, and one gets shot out. If these planets are away from any other gravitational force, it is quite hard to measure their mass, except there is one technique we can use. So my tea's going to get cold. So we know that objects with mass are going to bend space-time, and everything traveling through the universe is going to follow the curvature of space-time. So if you have a really massive object that's distorted space-time, light is going to bend around this object. If you're looking at light coming from a distant galaxy, on its path towards you, this light is going to be distorted around some massive object. So in the scenario now, there's me, there's a massive object, and the other side of the massive object, or far away, there's a galaxy. The light from this galaxy is going to be distorted and bent around the massive object. This is what we call gravitational lensing. So then when we look at the light coming from this galaxy, we're either going to see a very deformed light, as if somebody's held up a lens in front of it, or we're going to see multiple images of the same galaxy because of the way the light is distorting around this massive object. And by looking at how much light is distorted, we can get an idea as to how massive the object in between us and the galaxy is. And I am looking for an image here, but apparently it is quite far behind in my slide deck, so it's taking me quite a while to get there. And here is the image I wanted to show you. This is gravitational lensing, just explained a bit better. So you can see a galaxy in the background. It's emitting these kind of white light beams. These white light beams on their path towards us, we are here in the bottom left. These light beams will encounter a gravitational object, which is what you can see here in the center of the screen. This will cause the light beams to be distorted. So then when they reach us, we trace them back with these orange lines, and then we get two images of the same galaxy, two distorted images or multiple images of the same galaxy due to the gravitational lensing. Now, one cool thing about gravitational lensing is we're pretty sure we know how light behaves in the vacuum of space-time. So if we're able to get accurate pictures of these galaxies, then we can use that to infer the mass of the object in between. Now, this works well for big, massive objects, like big clusters of dark matter, or big galaxies. But on the scale of a rogue planet, it would be very, very difficult to actually have any type of gravitational lensing, because rogue planets are going to be a tad too small for that. We can then have what we call micro lensing, which, as the name implies, is a tiny amount of lensing, which is hard to detect, but which we can detect. And using things like micro lensing is how we can say, okay, probably dark matter is not black holes, because if all of dark matter was the size of black holes, we would see more micro lensing than what we see. So that is also how we do that. So to answer your question, how do we measure the mass of things in the universe? It's not exactly your question, but I'm paraphrasing here. We can see how its motion, how it affects other bodies. We can see how light is distorted around it. And if it's an object that emits light, for example, a star, in a way where we can measure its temperature, then we can relate its temperature to its mass if we know the relationship well. So there are several different techniques we can use to measure the mass of an object. Those are overall the most common ones that we would use. So getting to the level of a rogue planet is quite hard. For a rogue planet, we either need very precise micro-lensing measurements or really the rogue planet to be close to something else, in which case it's probably no longer a rogue planet. I assume there's advanced computer programs that work backwards on those lens images. Absolutely. There's a lot of... So extracting information from these lensing maps is extremely difficult. There are a bunch of surveys out there, so telescopes collecting a huge amount of data, that are collecting precisely this lensing stuff. And it gets more complicated because you have different types of lensing. Like you can have galaxies that are lensed, you can have galaxies that are sheared. Of course, you also need to get an idea as approximately how far away these galaxies are in order to really understand the shape of the distortion. So you ideally want the redshift or the distance to the galaxies and their exact shape. And then you need to stack this because of all the galaxies you're getting. So analyzing and processing lensing data is extremely difficult. In fact, I was at a conference in the summer in Sisto in the Italian Alps. It's an incredible conference. We were talking about the cosmological tension, so the Hubble tension, which is basically asking the question of how quickly does the universe expand. We're trying to figure out how best to answer that question, but one way you can go over. And the other question we were asking is how much matter clusters on specific scales. For the second one, you can use lensing, or you can use a CMB. And depending what you use, you get a slightly different answer. Very small difference, but a slightly different answer. So I was at this conference. That was a whole week where we brought they brought experts together on all of the different topics. We basically spent a week trying to figure out what is the current status of this inconsistency and how do we solve it. And my biggest takeaway from that conference was that understanding lensing data is ridiculously difficult. And the people who work on it do an incredible amount of work and effort in order to really understand this different type of lensing. So yeah, there's computer software that you use. There's a bunch of methods and statistical processes that you use to try to understand this. And it is a very, very, very difficult process to understand. So it was a really cool conference, actually. We spent, I think the first day was entirely about Cmb Physics. So Cmb is obviously the cosmic microwave background radiation, which is the oldest light we can see in the universe in any direction we look in the night sky. And I am absolutely doing this as an excuse to flash this image of the Cmb. Oldest light we can see in the universe in any direction you look in the night sky. It is the afterglow of the Big Bang. Based on the hot and cold spots, these tiny, 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 tiny temperature differences, we can learn a lot about the universe. One thing we can ask the CMB is how much does matter cluster on specific scales? And this whole thing of how much does matter cluster on scales, we call S8 or sigma 8. If we ask the CMB, we get one value. If we ask these weak lensing experiments, we get a slightly smaller value. The difference is very small, but noticeable. So at this conference, we spent one day just talking about CMB. We spent a few days talking about lensing from multiple different perspectives, a few days quantifying the problem. Now, I know that it was only 5 days, but it felt like we did a lot of stuff. And then some days talking about possible solutions, and that's when I gave a talk as well. So your question there about, are there different computer codes to do this? Yes, there are. But understanding lensed images is a very, very complicated topic. Hey Hamza, great to see you. Nice to see you in the audience here. As always, feel free to ask any questions you want. This is an interactive stream. If people don't ask questions, I get to ramble. Today, I just found a random reason to bring up the CMB, and it took me 28 minutes today, so you should be impressed. It took me a long time today. Going back to some comments that I missed just now. The concept of terraforming Venus is cool. It would be. The problem with Venus is it doesn't really have a decent atmosphere, which means it's very, very difficult. It's very difficult to do any type of terraforming on Venus because first you need to build an atmosphere and then you need to make the planet livable. But it would be pretty cool, but also pretty hot actually, given where Venus is. Comment here about Star Trek Enterprise. You know, to be honest, I have not watched as much Star Trek as I should. Given that I am in fact named after Deanna Troi from Star Trek, you'd expect that I would have watched more Star Trek than I have. I've watched a few of the original films. I've watched some of Picard's era, not the new Picard series, the original. I think I watched some of Genesis. Can't even remember what I have and haven't seen, but to be honest, it's been a very long time since I watched Star Trek. I watched the new films, didn't like them. I watched 2 episodes of Picard, couldn't get into it. But I'm sure there's a Star Trek episode where they find a rogue planet, because they find everything. So probably, but I'm not up to date with my Star Trek viewing. Okay, missed a few comments there. Let's go back to what I just missed. Where were we? Here we were. Comment from Scott. I remember hearing that Andromeda is red-blue shifted because of its rotation. I thought there's no way it rotates fast enough for that to be a thing. That is an interesting point of view. So we always do have a thing that, you know, if you're looking at a galaxy, every galaxy is rotating. right? So part of the galaxy is going to be moving away from you, and part of the galaxy is going to be moving towards you. Now, usually this is a minor effect. When we look at distant galaxies, the bigger effect here is the distance to the galaxy. The further away they are, the more redshifted they are. This is something we know as Hubble's law. So usually if you're looking at very distant galaxies, the dominant redshift contribution comes from the distance because the rotation is really, really small. Now, Andromeda is the closest galaxy to the Milky Way. Andromeda overall is actually blue shifted. It is getting closer to us. Redshift means something is moving away. The light waves are compressed towards the light waves are stretched towards the red end of the electromagnetic spectrum. If something is coming towards you, it is compressing the light waves and they move to the blue area. Andromeda is on a collision course with the Milky Way, which means overall it is blue shifted. Now, I guess if you look at the left, like the different parts of Andromeda galaxy, you will get a slight red shifting in one and blue shifting in another direction based on the rotation of Andromeda. But overall, I think the dominant contribution is still going to be the distance between us and Andromeda, because the distance between us and Andromeda is much larger than the size of Andromeda. So when you're looking at the individual rotation of the galaxy, what you care about is how big the galaxy is. But when you're looking at the overall redshift or blue shift, it's the distance to the object that matters. And the distance to Andromeda is much higher. So while there is probably this effect that depending where you look in Andromeda, the redshift might change very, very slightly, I think it is not going to be the dominant effect. But that is a really, really interesting point, Scott, and one I actually haven't thought about in quite a while. Okay. Regarding Venus terraforming, you were referencing the course gazette. Yeah, the thing is, there are so many cool course gazettes, but they do have one about terraforming Venus. They also had one of what would happen if the moon crashed into the Earth. That was fun. Okay, going back, there was another question here by James that I missed. Is it even possible for a telescope like the Just Wonderful Space Telescope to point to a space and not see anything? Not really, because there are assuming it's looking in the right frequency band, right? If you point a gravitational wave telescope in the background, you might not see anything. Now, if you point an we will. LISA is going to see stuff. You know, don't let me say that. LISA is going to see stuff, definitely. But given the huge amount of objects in the universe, it is quite likely that if you just point your telescope into the night sky and stare long enough or let enough photons hit you, you are going to see stuff. There are a few places where you could stare and see nothing. There's this random, like, dark blob somewhere in the universe that you can see a lot of stars and just a black blob. And no one really knows where this void comes from. But there are voids. In between galaxies, there are voids. But from here, if you're looking out, you're always going to have stuff within the Milky Way and beyond. So it would be very, very difficult for a telescope such as Hubble or the Just Wonderful Space Telescope to look out and not see anything. Because there's just so much out there to see. You know, the universe is huge. There are billions and billions and billions of stars out there, and so many galaxies, and there's so much out there we can see. I see a CMB question down there. I love the CMB question. Oh, hi, Paul. Didn't see you come in. Nice to see you, and a late hello to you as well, Paul. Okay, CMB question, and then black holes. So, question from Nadia here. Are there ways the CMB could be used to narrow down multiverse hypothesis? I love this question because it has a CMB, but in general, it's a very nice question. So, the multiverse hypothesis is this idea that there are multiple different universes out there. And it's possible that in each one of these universes, the laws of physics are slightly different. Now, in sci-fi, this is often taken to the extreme of every time you make a decision, you have a different universe, this is a specific interpretation of quantum physics that may or may not be valid. But from an inflationary standpoint, you can take the idea that in the early universe, there was this exponential expansion, and maybe this expansion happened in pockets, and each of these pockets had its own amount of expansion or rate of expansion, and this would naturally lead to pocket universes where the laws of physics are very slightly different, and this is known as a multiverse. Now, the thing is here, we are limited to the information contained in our own universe. So trying to access information from any of the other multiverses, if they even exist, is very, very difficult because it's disconnected from us. The whole point of how these multiverses form is, if they do form at all, is that we cannot connect to them in any way. So it then becomes very, very, very difficult to gain any type of information about the multiverse. However, dramatic pause for tea drinking there. If we look at the CMB, this cosmic microwave background radiation, if you imagine this is a clock and you look kind of where I am, so just up here, just very slightly kind of up here, imagine my finger extending right where I'm pointing here. Hope you can see me on the screen pointing in the right place. There is this region that is slightly bluer than the surroundings. And this is known as the blue spot or the cold spot. It's a region on the CMB where the photons are slightly colder on average than everywhere else. This is something that there's a lot of different possible explanations for, and one of them is that this is an imprint from another multiverse. So this is one hypothesis here, that this cold spot could be kind of where these multiverses are slightly pushing together. However, with the Planck 2018 data, this no longer seems like a favorable hypothesis. Now, it's not something I've worked on. It's not something that I know too much about, but there was this idea that we could use this specific cold spot of the CMB as a kind of constraint for some potential multiverse. However, currently, it doesn't seem to be compatible with the idea of two multiverses brushing into each other. There's also a lot of theoretical problems here. So how would this be stable? How would they touch without collapsing into each other? You know, imagine you have two multiverses where the laws of physics are slightly different, where you have a very slightly different value for the Higgs potential. Now, the Higgs potential is related to the Higgs boson. It gives everything mass. It's probably in a metastable state, which means at some point it could directly tunnel into a lower vacuum state and create a vacuum death of the universe, and we'd all die in the blink of an eye without even seeing it coming. Fun. Expanding bubble of death, known as the vacuum decay of the universe. Point being, if we are in one Higgs metastable state and we were to come in contact with a multiverse where there's a slightly different metastable Higgs, then the Higgs, whichever one is higher, would tunnel to the lower value immediately. So having multiverses come into contact would probably be very problematic. So it comes back to the idea that the multiverse is a hypothesis that is very, very difficult to study in any way. But if you'd heard some things about the CMB and the multiverse, it was probably through the blue spot, the cold spot here. So that is a very nice question, Nadia. I've realized on my streams, I often do the thing where I forget about my tea, and then at the end of the stream, I have a cold cup of tea. So now I'm making a point to actually drink my tea before it gets too cold. Okay. Next question, interesting question from Paul here. I heard black holes grow mostly when they merge after galaxies collide. But if a black hole is a small percentage of a galaxy mass, wouldn't it grow more from other stars in that galaxy rather than just other black hole? So this is a great question here, Paul, and I'm not sure if you're referring only to black holes or to supermassive black holes here. Now, black holes grow by having stuff fall on them. Black holes are regions of space-time that are so dense that you'd have to travel faster than light in a vacuum to escape. To our knowledge, nothing can travel faster than light in a vacuum, and therefore nothing can escape the gravitational pull of a black hole. But the thing about black holes and the thing about gravity is very, very, very weak. You know, we think of gravity as being this really strong force, but it is the weakest of all forces, apart from the weak force. But it's weaker than the weak force. Just had to make a stupid pun there. And the thing is, gravity falls off with the distance squared. So if you increase your distance to an object by a factor 10, the gravitational force falls by a factor 100. Which means that while black holes can accrete a lot of things, they can have a lot of things falling on them, not everything is close enough to fall onto a black hole. So then you require objects being close enough to fall into the black holes. This brings us to the supermassive black holes at the center of every galaxy. So at every galaxy, we believe at the center there is a supermassive black hole. And these supermassive black holes are not going to suck up the whole galaxy. because a lot of the galaxy is too far away to really feel the gravitational, so it feels the gravitational presence of this object. But in the same way that we are not dramatically falling into the sun, the orbit is decaying slightly every year, but not dramatically. Not everything in a galaxy is going to fall into the supermassive black hole at the center. The supermassive black hole is going to eat some things up, but at some point it reaches a saturation point. Now, if you have two galaxies smashing together and their black holes come close enough, these are going to swirl around and merge. So then there is the question, let's go back to your question here. Black holes grow mostly when they merge after galaxies collide. This is overall true because the amount of matter they accrete from close by objects is not really too much because most things in the galaxy are not close enough. So yeah, it's mainly when they smash together. But now we can get to the fun question. We can get to the fun question here of what came first, the galaxy or the supermassive black hole? Do galaxies form around supermassive black holes because you naturally have an accretion disk? Or does the fact that you have a galaxy produce a supermassive black hole at the center? We don't know this question. So as to what came first, the supermassive black hole or the galaxies around it, we don't know. And I think that's really, really cool. Then you could say, like, you know, I'm pretty sure we named galaxies before we named black holes. So linguistically, galaxies came first. But from a physical standpoint, we don't know if galaxies came before black holes or if the supermassive black holes came before the galaxies or not. So that is pretty cool. So I hope that answers your question there. Usually, to the best of our knowledge, supermassive black holes grow a lot when they smash together into another supermassive black hole. And this is one of the things that we hope that LISA will measure. LISA is a Laser Interferometer Space Antenna, the space-based gravitational wave mission set to launch in the 2030s, and is going to measure gravitational waves coming from amazing stuff in the universe, such as supermassive black holes smashing together, and potentially LISA will help us measure the cosmic ripples in the background of the universe coming from the processes that happened in the first fraction of a second after the Big Bang. And that is what I'm working on, and that is ridiculously cool. And I'm not going to go into that now because I've done about 4 streams on this topic by now. But yeah, hopefully LISA will also help us understand more stuff about supermassive black holes, because it should be able to measure gravitational waves coming from supermassive black holes smashing together. Okay, follow-up on the telescope question. So the telescope question before was, if you point a telescope randomly in space, will you ever find a region where you don't see anything? My answer was no. And now you ask would my answer be the same if we're only looking at visible light? Now, I think this comes down to the question of how big is your field of view, right? So we know that in between galaxies there are voids, and if you point a telescope into the void, you're not going to see much. But then you still get the light coming from behind the void, because light has the tendency to just keep on traveling in the universe. It doesn't really stop. There's not much that can stop light traveling in the universe. So even if I'm looking at this big giant cosmic void here, behind the cosmic void, there's going to be stuff that is sending light. So even if we only have a visible telescope, so a telescope working in the visible light range, I think unless you actually point it like in a direction, so most places you look, now I think everywhere you look, you would still see light. Now, of course, then if you're trying to really peer back into the distant past when everything was in a different range, then it becomes harder. But yes, my answer still stays the same, I think. In any direction you would point the Hubble Space Telescope, which is our optical telescope, the best one we have, in any direction you point it, I think you would see light. But then, of course, it depends on the resolution and the aperture and how much light you're receiving. If you just swing it by, you're not going to pick anything up. But if you park the telescope and let photons fall into the telescope, you will see things, I think, in every direction. I'm happy to see counter arguments to that, but currently my answer stays the same. You thought galaxies formed around dark matter? They do. That is to the best of our knowledge. But when do supermassive black holes come into the play here? So dark matter sets the scaffolding upon which galaxies can form. But does the dark matter also then produce, so not the dark matter producing, but if you have the huge gravitational presence can you automatically form a supermassive black hole and then the galaxy gradually accretes behind it? Once you have a bunch of stars in one place. So what we want to understand here, the question is basically, how do we go from having a bunch of dark matter and stars to having a galaxy with a supermassive black hole at the center? So there are several different processes that can happen here. For an example, you could have black holes together in this mix where you have dark matter, you have stars, you have some black holes because stars start dying or because they crash together enough, and you end up with black holes. Then could one of these be like the seed around which the rest of the galaxy starts getting structure? So they do form in places where there is more dark matter. But the way we go from stars and dark matter to a galaxy with a supermassive black hole at the center is not completely well understood. So there are several different hypotheses as to which direction we could take, but it is not completely understood yet. I did have Sofia Gatnaza on my show at some point talking about supermassive black holes, dark matter, and galaxies. That is actually the next one I plan on uploading to YouTube. So the next weekend when I can't do a live stream, I will upload that replay because it was really, really cool video, and that one's not yet uploaded, but I will fix that soon. So billions of years ago, were there just stars evenly dispersed and no galaxies? Well, not evenly dispersed, because the stars were clustered around where we have dark matter, because that's where the hydrogen was clustered because of the gravitational force. So you have dark matter, hydrogen is going to fall where the dark matter is, you're going to start forming stars, and at some point this cluster of stars is potentially going to become a galaxy. But we know there are regions of stars that are not galaxies, for an example, nebulas. If you have, for an example, in the Karina Nebula, let me find the Karina Nebula because I have this amazing image from the Just Wonderful Space Telescope, and it's in my image deck, so I might as well bring it up. So we have this amazing image here of the Karina Nebula from the Just Wonderful Space Telescope. And what you can see here is a lot of young stars, so a lot of new stars forming. Now, of course, you could argue, yes, these are part of our galaxy, absolutely. But by themselves, this cluster of stars is not going to break off and form a new galaxy. So you can just have stars dispersed that are not part of a galaxy. So then the question as to how we went from having stars dispersed to having galaxies, this whole galaxy evolution and galaxy formation is something that there's a bunch of people working on, and I am not one of them. But at some point, you did just have like clumps of stars and dark matter, and then these became galaxies. Not all at the same time. It wasn't every star just unanimously decided, let's unionize and create galaxies. Although unionizing is always a good plan. And of course, I had to get political. Join your union if you can. So, like the stars join galaxies, join your union. Anyway, it wasn't everyone at one point just randomly decided, let's form galaxies. So at some point, we have stars and dark matter and a galaxy forms, and this happens elsewhere in the universe. And in multiple places, you're going to end up forming these galaxies. But in between, there is a stage where you just have stars and not a galaxy. There's this transition phase. So yes, you did have these kind of clouds of stars that at some point became galaxies. Clouds of stars and dark matter that became galaxies with supermassive black holes at the center. And I do want to go back to the comment from Scott here, the one in all caps. And my tea is gone now. So I just made this offhand comment that our orbit is gradually decaying and we are gradually falling into the sun. And of course, this is something that might sound a bit perturbing or a bit worrying. Like, are we going to fall into the sun? So, any two objects that are orbiting around each other are going to be producing gravitational waves. These gravitational waves carry energy away from the source. If they carry energy away from the source, then the whole system has to lose energy. And the way it does this is by the objects getting slightly closer. So if you have two objects orbiting around each other, they are gradually going to get closer and closer. In the case of black holes, when we have the two black holes orbiting each other, eventually they are going to collide and merge and produce a huge burst of gravitational waves, which is what we can then measure here on Earth. We've seen this with black holes, we've seen this with neutron stars, we've seen it with black holes smashing into neutron stars. But this happens for any two bodies. So if you take the system of the Earth and the Sun, we are orbiting around the Sun, but we are also producing a very, very, very small effect on the Sun. All objects, for every action, there is an equal and opposite reaction. When you factor in the difference of masses, the action the Sun is doing on us is orders of magnitude bigger than what we are doing to the Sun. But we are still making this tiny, tiny difference. So while we are in orbit around the Sun is also moving very slightly because of us. What this means is that you basically have two objects orbiting around each other. So the system between us and the Sun is producing gravitational waves. At the same time, this means that the Earth is getting gradually closer to the Sun. But there is no need to worry, because this is a very, very, very tiny effect, to the point that in the entire history of the solar system, since Earth has been here, our orbit has decayed, so we have got closer to the Sun by about 1 meter, based on these gravitational waves that we are producing. This is something we can calculate based on the Sun's mass and the Earth's mass. So while, yes, our orbit is gradually decaying, this gradually is insignificant. When you consider that between us and the Sun, on average, there are 10 to the 15 meters. So that's a 1 followed by 15 zeros. So that would be what, a billionth, 1,000th billionth. So that's how 1,000 billion. That's how many, I think the word at that point is like a quadrillion or something, or sextillion. But at this point, it's a very big number. So 1 or 2 meters is not going to be a big difference. So while we are decaying in our orbit and we are gradually getting closer to the Sun and producing gravitational waves in the meantime, it is such a small and meaningless effect that we do not need to be worried about it. But it's a fun thing to throw out there, that technically our orbit is decaying and technically we are falling into the Sun, but at such a slow rate that it's not something that we need to concern ourselves in our lifetime. Before we fall into the Sun is going to expand and eat up the first 3 planets, and potentially eat up our orbit as well. So we don't need to worry about falling into the Sun. The Sun is going to kill us long before that, unless we kill ourselves first. So comment from Paul here, we smashed a dark probe into an asteroid to affect its orbit. Maybe it will retaliate and deflect ours. Yeah, so this is a really cool thing that we have these 2 asteroids close together. We sent a little satellite to smash into one and bump it just very slightly, just to see if we can. Now, the good thing is that while this asteroid is big, and we did actually disrupt its orbit by basically throwing something at it, it is a very small asteroid compared to the size of the Earth. Now, of course, hopefully it's not going to decide to retaliate. If it's sentient enough to do that, we have problems. But it's really cool. This is like a first line of defense type thing. If you buy into all of the military speak and the defending the Earth type thing, it's just really cool that we've been able to deflect an asteroid slightly. Because in the future, in the event of an asteroid hurtling towards Earth, we know there have been these catastrophic events in the past. They might happen again. If we do eventually find an asteroid on a collision course to Earth, we might, if we have enough warning, we might be able to divert it. And DART was the first test. DART was the first test towards seeing how effectively we can disrupt the orbit of an asteroid, and it was highly successful. So we basically threw a satellite, or threw a little baby spacecraft at an asteroid and slightly flicked it. It was really, really cool. And as Paul says, if any aliens are watching, they will just think that we are very bad at navigating. Question from James here about the multiverse. When we refer to multiverse, is it a separate universe with no connection to ours, or is it a variation of ours? So this very much depends on what type of multiverse you're talking about. The one that I often think of if I think about multiverse is in the early universe. You have bubbles of inflation that produce different universes, slightly different laws of physics, and these are what we will call multiverses. And this is something that a lot of people think occurs naturally in the early universe. This is one type of multiverse. Another thing you can think of is the idea that until you observe something in quantum physics, it is undetermined. And one interpretation of quantum physics is that every time you make an observation, the universe splits with each possible action taking place. And this is the one that is exploited in sci-fi, that every decision you make branches off new universes, and this is what is done in sci-fi. So personally, when I talk about the multiverse, I'm usually thinking of these pocket universes with slightly different laws of physics that can occur naturally in many inflationary models. But in sci-fi, it's much more usually thinking about these multiple possibilities, because it just gives people more fun, more things to play with. But in any case, all multiverses are hypothetical, and we are limited to the information contained in our own universe. So even if there are other universes out there, it would be very, very difficult for us to ever have any type of contact with these other multiverses unless you're in the realm of sci-fi. Okay, comment from Nadia. The sun will be an iron star before the Earth lands on it. Yes. So when the sun reaches the end of its lifetime, it's going to grow as a red giant, and it's going to engulf Mercury and Venus. We're not yet sure if it will also eat up the Earth, but in any case, it will get big enough and close enough that it will completely scorch the Earth. And this will happen in about 4.5 billion years. And by then, the Earth-Sun decay from gravitational waves is going to be another few meters at most. So we don't need to worry about us falling into the sun. We do need to worry about the sun expanding and coming to grab us. Again, we don't really need to worry about it because this is 4.5 billion years in the future. So it's not something we need to be worried about on a day-to-day basis, but it is something very interesting to think about. It's cool to think about what's going to happen 4.5 billion years from now. Ever hear about Project Thor? The US government studied the feasibility of using giant rods of tungsten to wage war as opposed to ICBMs. I have not heard of Project Thor, but sure, if people can make it work, I'm sure if anyone's going to try to investigate ways to kill each other, it's going to be the US military. But yes, I have not heard of Project Thor, but I'm not a huge fan of superheroes, but I do like Thor. But no, I haven't heard about Project Thor. I'm not really sure how you would use tungsten to fight, but that's why I'm not an expert on weapons. I was hoping for multiverse me paying less rent. Yeah, the thing is, if there is a multiverse version of you paying less rent, we're in the realm of sci-fi here, you will never be able to chat to them. So, they don't, there's probably a version paying less than them. There's probably a version paying more than you somewhere as well, if you subscribe to this idea that there are an infinite amount of universes. But unfortunately, or fortunately, depends on your point of view, we are limited to the information contained within our own universe, and therefore any type of multiverse or any type of other version of you that exists out there in the universe, in the multiverse, is probably locked away from you and inaccessible. So don't wait for the you from the multiverse to save the day. If you want to make changes, do it yourself. Don't wait for a multiverse you to help you out there, because you'll probably be in for a very long wait. But it does give people a lot of freedom to play, and this is one of the reasons that sci-fi authors really like the multiverse, because it's just a lot of fun, a lot of possibilities, a lot of hypotheticals you can go down. Some do it well, some do it less well, but that's sci-fi for you. Okay, I do believe I answered all of the questions that came in the chat today, I think, yes. Another one here, if you add up all the different views in the multiverse, that's a lot of rent, yes. Fortunately, each one is paying their own rent. There's going to be multiverses out there. If we subscribe to this, there will be multiverses out there where rent doesn't exist and where landlords don't exist, and that's perhaps one we should have tried to emulate. Some criticism of space exploration is that it's dual use for missile targeting. There's always a problem with space exploration in that in order for it to be done properly, we need to move away from the colonial mindset we have currently. Currently, any country trying to do space exploration, I would be very concerned about. It's great for humanity that we're going to go out there into the stars, and then suddenly you have people trying to privatize the moon and privatize the night sky. There's also this whole idea of what gives us the right to go and disrupt other things in the universe. So I'm all for space exploration. I'm all for pushing boundaries and going out there in the universe, but we need to do it from an ethical, decolonialized point of view, and we are not there yet. Best multiverse movie, Everything Everywhere All at Once. I've heard a lot of people say good things about that one. I have not yet got round to watching it. So it is on my list. But yes, Everything Everywhere All at Once also kind of feels like academia sometimes, everything happening all at the same time. But it is a film, and I'm sure a lot of other jobs as well, actually. That's not purely an academia thing, just a life thing. But yes, I've heard very good things about that film, and it is absolutely on my list. According to Doctor Strange, you know that's not going to be a great sentence. According to Doctor Strange and the Multiverse of Madness, food is free in most universes. To be honest, food should be free. Food, housing, basic human rights should be free. Living should not be a commodity, right? Living is a basic human right. Food, education, roof, housing, all of these things I think are basic human rights, and they should absolutely be free. And that is something we should try to fix in our universe, or at least in our planet. Okay, so ignoring the slightly political rants that I always slip in at some point, we have reached the 1 hour mark, so it is time to wrap up Cup of Cosmology for this week. Thank you everyone for being here. There's been some really fun questions, and I'm happy that today you didn't hit me with tough fundamental philosophical questions, because the last few times when I've come here without a topic and done an improvised stream, I've been hit with really difficult questions like, how does the strong force work? I've still got a note to look that up, and I love those questions because they throw me off. And I was actually saying to someone before coming on the stream today, I wonder what random fundamental question they're going to hit me with today that I won't know the answer to, but I was able to answer all of the questions today, so thank you for that. But obviously I love all of the deep questions people ask, and you can always ask me anything here. So I do love all of the deep questions. Do keep them coming. But it was nice to actually have some really cool questions today as well that didn't really make my brain hurt. I like questions that make my brain hurt, but it was also nice to have great questions today as well. So all types of questions are always welcome here. And today we had some really fun ones, more focused on exoplanets and terraforming stuff, Dyson spheres, and there was the Cmb question. Always keeps me happy. October shows are definitely not 2 hours. I'm not sure where you heard that, James, but that is not happening. I've been speaking now for 1 hour. My voice is already tired, and tomorrow I'm giving a presentation. So I should be ready for my talk tomorrow, which means I cannot lose my voice today. So today we are absolutely not going for another hour. But I should be online next Sunday, same time as usual. That's 8 p.m. Helsinki time, 7 p.m. Central European time, 1 p.m. if you're on the East Coast, and 10 a.m. if you're on the West Coast. And that will change in 2 weeks when we start doing daylight saving time. We'll get rid of daylight saving time, but next week should be same as what you're used to. So I should be back online next week. I currently don't have a topic or a guest or anything planned for next week. We will figure that out as we go. Or maybe I just wing it again. I'll see you next week. As usual, if you haven't done so already, please like this video, leave a comment, subscribe, do all of the usual YouTube things. And if you're on Twitter, please go and subscribe to the YouTube channel as well. It's how I build the audience. It's how YouTube keeps promoting my videos. It just adds engagement. So please do all of the usual YouTube things, press all of the right buttons. I will see you all again next Sunday, same time as always. And in the meantime, I hope everyone stays safe and take care of each other.